The universe began as a prison for light. For nearly 400,000 years, not a single photon could travel freely through a searing, opaque fog of creation. Then, in a single cosmic moment, everything changed. This is the story of the Epoch of Recombination, the instant the cosmos became transparent and the first light escaped. By the end of this journey, you will understand exactly how we can see the afterglow of the Big Bang itself. We will uncover what triggered this sudden clearing of the cosmic haze and how the faint whisper of that first light holds the blueprint for everything that followed, from the first stars to the galaxies we see today. What does it feel like to look back and witness the very dawn of the universe? That dense fog was the universe's first and most fundamental state. For nearly 400,000 years, it was a place of unimaginable energy, a searing plasma where temperatures soared beyond comprehension. The entire cosmos was a chaotic soup, a roiling sea of fundamental particles. Protons, electrons, and photons were all trapped together in a frantic, constant dance. A photon, a particle of light, could not travel even a tiny distance without slamming into a free electron, being scattered and deflected in a new direction. Light was utterly imprisoned within this thick, opaque fluid of matter and energy. This was the Photon-Baryon fluid, a state where light and matter were inextricably linked, creating an impenetrable cosmic haze. But this chaotic condition could not last forever. The universe was expanding, and with that expansion came a profound and inevitable cooling. As space itself stretched, the energy density of that primordial soup began to drop. The particles, once packed with ferocious energy, started to slow down. The temperature fell from billions of degrees to a few thousand, a critical threshold that would change everything. This cooling set the stage for a monumental shift, a process so pivotal it is called recombination. The name is a little misleading, as if things were combining again. In reality, it was the first time electrons and atomic nuclei could ever peacefully unite. Until this point, the universe was too hot and violent for such stable unions. Free electrons with their negative charges were constantly repelled by the intense energy of photons, preventing them from settling down with the positively charged protons. But as the cosmos cooled, the particles finally lost their frantic energy. Electrons could be captured, orbiting atomic nuclei to form the simplest, most neutral atoms, primarily hydrogen and helium. This single event, the formation of the first neutral atoms, was the key that unlocked the universe. It broke the constant scattering between light and matter. Suddenly, the fog lifted. Photons that had been bouncing around for millennia found themselves with a clear path. For the first time in cosmic history, light could escape, streaming freely across the expanding darkness. This was the moment of transparency, the great liberation that set the stage for everything to come. Think of a pot of boiling water left to sit on a stove. At first, it releases a thick, billowing steam, an opaque cloud where you cannot see through. But as it slowly cools, the water vapor condenses back into liquid droplets, and the air gradually clears. The early universe underwent a transformation eerily similar to this. It began not as a void, but as an impossibly hot and dense point, a singularity. The initial event, the Big Bang, did not explode into space, but rather was an explosion of space itself, a rapid, relentless expansion that stretched the very fabric of the cosmos. This expansion was the primary engine of cooling. In its first moments, the universe was a searing broth of energy at temperatures of trillions upon trillions of degrees. But as space stretched, that immense energy had to fill a vastly larger volume. The temperature plummeted, falling over hundreds of thousands of years from those unimaginable heights to a relatively tepid few thousand Kelvin, similar to the surface of a cool red star. This cooling was not random or chaotic. It followed a precise mathematical rule dictated by Einstein's theory of general relativity. The temperature of the universe dropped in perfect inverse proportion to its growing size. As the cosmos doubled in scale, its temperature was cut in half. This steady, predictable cooling had a direct and dramatic effect on the particles trapped within. The photons, the particles of light, were stretched along with the expanding space. This stretching caused their wavelengths to lengthen, shifting them toward the red end of the spectrum in a process we call cosmological redshift. With this redshift, the photons steadily lost energy, becoming less and less powerful. At the same time, the density of the particle soup was dropping. Particles were simply farther apart, so the frantic, constant collisions that defined the early plasma began to subside. The chaotic thermal motion that had kept electrons and atomic nuclei violently apart was finally being overcome by a more fundamental force, the attractive pull of electromagnetism. Experts like physicist Alan Guth have highlighted how this precise cooling created a perfect cosmic doorway. It was the slow turning of a dial, lowering the energy enough for a fundamental shift to occur. What if that expansion had been slightly faster or slower? A faster expansion might have cooled the universe too quickly, potentially altering the delicate balance that allowed atoms to form and thus life to eventually emerge. This gradual, inevitable cooling set a perfect stage. It prepared the universe for its next, most critical act, the moment when matter would finally snap into a stable form and release light from its ancient prison. Long before the fog could lift, the universe had to forge the very building blocks of matter itself. This cosmic forge operated for only a few fleeting minutes, yet it set a chemical legacy that would last for all time. In the universe's first 3 minutes, the conditions were perfect for a brief, spectacular burst of creation. The temperature had cooled from its initial unimaginable heat to a mere billion degrees, a point where nuclear fusion could briefly occur. Protons and neutrons, which had previously existed as a free particle soup, began to collide and stick together. This was the epoch of Big Bang nucleosynthesis, the origin of the universe's first atomic nuclei. The first and most critical step was the formation of deuterium, a heavy isotope of hydrogen. A single proton and a single neutron would combine, but this union was incredibly fragile. In the earlier, hotter universe, any deuterium that tried to form would be immediately blasted apart by a high-energy photon. But as the cosmos cooled past that billion-degree mark, photons finally lost enough energy that these tiny nuclei could survive. Once deuterium stabilized, it acted as a crucial stepping stone. It rapidly fused with other particles, forming helium nuclei. Trace amounts of lithium were also created in this frantic few minutes. The entire process was a race against time, as the universe continued its relentless expansion and cooling. Within minutes, the temperature dropped too low for any further fusion. The cosmic forge shut down, its work complete. The physicist George Gamow and his colleagues were among the first to realize this brief window was the only possible source for the light elements we see. Their calculations revealed a universe born with a specific chemical identity. About 75% of the ordinary matter by mass was hydrogen, the single proton. Nearly 25% was helium, the two-proton, two-neutron nucleus. Only the tiniest traces of lithium remained. We have confirmed these exact ratios by looking at the oldest stars in our galaxy, whose composition reflects that primordial mixture. This nucleosynthesis was not just about creating elements, it was about setting the stage for everything to come. The universe was now stocked with simple, stable nuclei. For the next several 100,000 years, these positively charged nuclei and their negative electron counterparts would be locked in the opaque plasma. But the simplicity of hydrogen and helium was key. Their straightforward structure meant that when the universe finally cooled enough during recombination, electrons could easily be captured into stable orbits, forming neutral atoms without complication. Had the early universe forged heavier, more complex elements, this capture might have been messy or even impossible. The precise balance achieved in those first 3 minutes ensured that when the moment of liberation arrived, the path was clear. The cosmic inventory was set, the raw materials were prepared, and the universe was now simply waiting for its temperature to drop one final, critical amount. That critical temperature threshold was just 3000 Kelvin. After hundreds of thousands of years of expansion and cooling, the universe had finally reached a state akin to a warm summer day, though it was filled with a sea of particles poised for a profound change. This was the era of recombination, a slow and meticulous process where the universe assembled its first stable atoms. Electrons, which had been wildly free for eons, began to lose their frantic energy. They could no longer resist the electromagnetic pull of the atomic nuclei that had been waiting in the plasma. One by one, they were captured, settling into stable orbits around protons to form neutral hydrogen atoms and around helium nuclei, known as alpha particles. This was not a single, instantaneous event, but a gradual transition that unfolded over tens of thousands of years. The process is beautifully described by the Saha equation, a piece of statistical physics that calculates the precise moment the balance tips from a charged plasma to a neutral gas. As the cosmologist James Peebles described, this was a delicate statistical dance. Photons themselves were active participants, mediating the transitions as electrons jumped between energy levels, sometimes being emitted and sometimes being absorbed in the intricate steps of atom formation. Selenium recombination actually happened a little earlier than hydrogen's because its electrons are bound more tightly, requiring a slightly higher temperature to break free. Yet even after this great neutralization was mostly complete, a tiny residual fraction of electrons remained free, a ghost of the universe's hot, dense past. The most crucial consequence of this atom building was the clearing of the cosmic fog. With electrons now bound securely inside atoms, the highways were suddenly clear. Photons that had been endlessly scattered now found very few free electrons to collide with. The moment a photon made its last collision with an electron, it was set free. We call this final interaction the last scattering surface, a cosmic boundary that marks the moment light escaped. The properties of this surface are forever imprinted on the oldest light we can see, the cosmic microwave background. How did the timing of this great clearing shape the patterns we see in our universe today? The answer lies in the journey of those first free photons, a story written in the faint afterglow that still fills the sky. These freed photons began an epic journey across the expanding cosmos. Their liberation was made possible by a fundamental shift in the balance of the universe itself, a moment scientists call photon decoupling. For nearly 400,000 years, light particles were trapped in a frantic dance with free electrons, a process known as Thompson scattering. Each photon would travel a minuscule distance before being deflected by an electron, bouncing around in a microscopic prison. The entire universe was a brilliant, opaque glow because of this constant, chaotic interaction. But then, the universe's expansion reached a critical point. The rate at which space itself was stretching finally surpassed the rate at which photons were scattering off particles. Think of a crowd so dense you cannot take a step without bumping into someone. Then the crowd begins to thin out rapidly, and suddenly you can walk in a straight line for miles without a single collision. This is precisely what happened to light. The optical depth, a measure of how easily light is scattered, dropped below a value of 1. This meant a photon could now travel a distance comparable to the size of the observable universe without being significantly absorbed or deflected. Its mean free path exploded from a microscopic scale to a truly cosmic one. This transition did not happen at a single, razor-sharp instant. The last scattering surface, the source of the oldest light we see, is actually a shell in space about 115,000 years thick. It is a fuzzy cosmic layer where the great majority of photons made their final encounters and then streamed away into the darkness. Nobel laureate John Mather emphasizes that the cosmic microwave background radiation we detect is a direct snapshot of this decoupling epoch. The tiny variations in its temperature, mere millionths of a degree, are imprints of the density variations in that primordial plasma. The slightly denser regions appear as cooler spots in the background, their gravity subtly tugging on the escaping photons and stealing a bit of their energy in a process known as gravitational redshift. This liberation was a universal event happening everywhere at once. Every point in space became a source of this freed light, creating a background glow that would slowly cool and redshift over billions of years until it became the faint microwave whisper we detect today with satellites like Planck. This ancient light carries more than just temperature maps, however. What secrets are hidden in its polarization? The very way this light waves can tell us about the universe's violent infancy, from gravitational waves rippling through space-time to the nature of the first atoms. The Great Escape was complete, and the dark ages of the universe were about to begin. The cosmos was suddenly flooded with a uniform, brilliant light. This was the first dawn, the release of the cosmic microwave background. Those newly freed photons streamed in every direction, saturating the universe with a primordial glow. In that first moment, this light was a searing white, a blistering wave of visible and ultraviolet radiation. But the universe did not stand still. Space continued its relentless expansion, stretching the very fabric through which these photons traveled. Over billions of years, this stretching systematically pulled at the light waves, lengthening them and draining their energy. The brilliant visible light was gradually redshifted down, first to infrared, and finally into the faint microwave radiation that permeates all of space today. This is the cosmic microwave background we detect, the oldest light in the universe, cooled to a mere 2.7 Kelvin, just a few degrees above absolute zero. Its spectrum is a near-perfect Blackbody curve, the telltale signature of an object in perfect thermal equilibrium. This precise match to a blackbody was a stunning confirmation of the Big Bang theory, a discovery that earned the COBE satellite team, including George Smoot, a Nobel Prize. The background is incredibly smooth or isotropic, appearing almost identical in every direction. This profound uniformity supports the cosmological principle, the idea that on the largest scales, the universe is homogeneous and looks the same no matter where you are. Yet, embedded within this smooth sea are tiny, crucial imperfections, minute temperature fluctuations, variations of only a few millionths of a degree, ripple across the sky. These anisotropies are not random noise, they are a cosmic blueprint. Each slightly cooler spot marks a region of the ancient plasma that was a tiny bit denser, its gravity pulling on the escaping photons and reddening them. These overdense seeds, amplified by the pull of invisible dark matter, would eventually collapse under their own gravity to form the vast cosmic web of galaxies and clusters we see today. Our own motion creates the most obvious pattern, a dipole anisotropy, where the sky appears slightly warmer in the direction we are heading and cooler behind us, like driving through a gentle cosmic rain. Even the polarization of this light tells a story. The E-mode polarization patterns are a direct imprint of the primordial density waves that sloshed through the Photon-Baryon fluid, a frozen record of those first acoustic oscillations. This cosmic fossil is our most powerful window into the universe's infancy. How exactly did those tiny temperature variations dictate the distribution of both visible matter and the mysterious dark matter that holds it all together? The discovery of the CMB revolutionized our field, and its continued study connects us directly to the sophisticated tools, from ground-based telescopes to space observatories, that now map its faint whisper. Those faint temperature variations in the cosmic microwave background are not random imperfections. They are the amplified echoes of the universe's very first moments, a direct imprint from a time when reality itself was smaller than a single atom. This profound connection between the quantum and the cosmic begins with inflation, a brief but spectacular period of hyper-expansion in the universe's first fraction of a second. During this inflationary epoch, the universe was a seething sea of quantum foam. At these unimaginably tiny scales, empty space was not truly empty. It was alive with quantum fluctuations, where pairs of virtual particles would constantly pop into and out of existence. These were microscopic ripples in the very field that drove inflation, the inflaton field. As the universe underwent its violent, exponential growth, these infinitesimal quantum ripples were stretched to proportions beyond comprehension. A fluctuation smaller than a proton in an instant became larger than a galaxy cluster. This process, as physicist Andrei Lind has described, provided a natural mechanism to generate the initial seeds of structure. The once microscopic irregularities were permanently imprinted onto the fabric of spacetime, creating a pattern of slightly denser and slightly less dense regions across the entire primordial plasma. This pattern is described by what cosmologists call the Harrison-Zeldovich spectrum, a nearly scale invariant distribution. This means that the fluctuations had roughly the same amplitude or strength, regardless of their size, from the scale of a single galaxy to that of a supercluster. It was this specific, gentle pattern of irregularities that gravity would later use as its blueprint. When we look at the detailed map of the cosmic microwave background, we are essentially seeing a photograph of these stretched quantum fluctuations, frozen in time at the moment of last scattering. The most prominent features in this map are the acoustic peaks, a series of hot and cold spots that correspond to specific harmonic oscillations in the early plasma. These oscillations were sound waves driven by the push and pull of gravity and radiation pressure. Imagine a region that began with a slight overdensity, one of those stretched quantum seeds. The extra mass of this region created a stronger gravitational pull, attracting even more matter. But this inward pull was counteracted by the intense outward pressure of the trapped radiation, the photons that were still coupled to the electrons. This created a rhythmic sloshing, a cosmic bell that was ringing. The overdense regions would compress, heating up before the radiation pressure pushed them back out, causing them to expand and cool. The fundamental mode of this oscillation, the first acoustic peak, corresponds to the largest distance a sound wave could travel in the plasma from the Big Bang until recombination. The precise scale of these peaks tells us the composition of the universe, revealing the amounts of ordinary matter, and dark energy. We also see direct gravitational imprints on this light. The Sachs-Wolf effect describes how a photon climbing out of one of those primordial gravitational wells, a region of higher density, must expend energy to escape. This energy loss manifests as a slight cooling in that part of the cosmic microwave background. Conversely, a photon falling into a well would gain energy, creating a slightly warmer spot. These effects are written directly into the temperature map we observe. Furthermore, the frozen remnants of those sound waves did not vanish. They left a permanent, faint signature in the distribution of galaxies, known as Baryon acoustic oscillations. There is a preferred scale, a statistical tendency for galaxies to be separated by a specific distance that corresponds to the size of that first acoustic peak. This cosmic ruler allows us to measure the expansion history of the universe with incredible precision. What if inflation had lasted for a different duration? A much shorter period might not have stretched the quantum fluctuations enough, leaving the universe too smooth for any interesting structure to ever form. A longer inflation could have diluted these seeds beyond recognition. The fact that we see this specific, subtle pattern of irregularities is a powerful testament to the intricate link between the quantum world and the grand cosmic architecture we inhabit today. The universe remained a brilliant, impenetrable fog for nearly 400,000 years because of a single, relentless physical process. A photon attempting to cross this primordial plasma behaved less like a beam of light and more like a pinball, constantly ricocheting off a dense sea of free electrons. This fundamental interaction is known as Thompson scattering. The probability of such a scattering event is encapsulated in the Thompson cross-section, a fixed value that tells us how large a target each electron presents to an incoming photon. When you multiply this cross-section by the incredibly high density of free electrons in the early plasma, you get an opacity so immense that a photon's journey was brutally short. Its mean free path, the average distance it could travel before being deflected, was staggeringly small, less than the size of a modern-day galaxy. This meant the entire observable universe was smaller than the distance a photon could travel before another collision. The cosmos was a perfect prison, maintaining a state known as thermal equilibrium, where matter and radiation were locked in a constant, energetic exchange. Physicists like Steven Weinberg described this as a universe where light was perpetually trapped, its energy continuously redistributed, creating that uniform, opaque glow. This relentless scattering did more than just trap light. It forcefully coupled photons and baryons into a single, unified entity, the Photon-Baryon fluid. Any slight lump in the distribution of matter, a region with a little extra gravity, would try to collapse, but the intense radiation pressure from the trapped photons pushed back, creating a powerful, rhythmic sloshing. These were sound waves traveling through the cosmic medium, and their frozen imprint is what we now see as the intricate pattern of hot and cold spots in the cosmic microwave background. The Great Clearing, the moment of transparency, arrived precisely when this scattering ceased. As electrons were captured into atoms during recombination, the number of free scatterers plummeted. The electron density dropped so dramatically that the opacity of the universe fell virtually to zero. The mean free path of a photon exploded, suddenly becoming larger than the universe itself. In that instant, the pinball machine turned into an open highway. The last photons to scatter off electrons streamed away unimpeded, and that final interaction surface, the last scattering surface, became a permanent snapshot of the infant cosmos. How do we, billions of years later, detect this faint echo from the dawn of time? This entire cosmic drama unfolded on a timeline of breathtaking precision. From its explosive birth to the great liberation of light, the universe followed a sequence of events as meticulously timed as the inner workings of a clock. If we were to compress the 13.8 billion-year history of the cosmos into a single calendar year, the moment light first escaped would occur around January 14th. The Big Bang itself is the very first instant of January 1st. In that first picosecond, a trillionth of a second, the universe was a unified superforce. Then, in an event known as electroweak symmetry breaking, the single force split into the electromagnetic and weak nuclear forces we know today. This created the distinct identities of photons and other particles, setting the stage for all future physics. Within the first microsecond, the universe had cooled enough for quarks, the building blocks of protons and neutrons, to condense out of the energy soup and become confined within them. This was the quark-hadron transition, the moment matter as we understand it truly began to exist. Just 1 second after the beginning, the universe had expanded and cooled so much that neutrinos, those ghostly particles, ceased interacting frequently with matter and streamed freely across the cosmos. This neutrino decoupling created a background sea of these particles that likely still permeates the universe today, a relic even more ancient than the cosmic microwave background. Then came the 3-minute window for nucleosynthesis, where the first atomic nuclei were forged. As the cosmologist Martin Rees has explained, this entire chronology is not arbitrary. It is tightly constrained by the fundamental laws of particle physics and Einstein's general relativity. The expansion rate, the particle densities, and the interaction cross-sections all had to align perfectly to produce the universe we see. A critical pivot point in this timeline occurred around 47,000 years after the Big Bang. This was the moment of matter-radiation equality, when the energy density of matter finally began to exceed the energy density of radiation. Before this point, the universe was dominated by the intense pressure of light, which smoothed out irregularities and prevented matter from clumping together effectively. After this crossover, matter, guided by the invisible scaffolding of dark matter, could finally begin to exert its gravitational will, starting the slow collapse that would eventually form galaxies. The period from nucleosynthesis to recombination was a long, quiet era of gradual cooling and expansion. The universe grew by a factor of over 1,000, and the temperature plummeted from billions of degrees to a mere 3,000 Kelvin. This specific cooling curve was essential. Had recombination happened earlier, while the universe was hotter and denser, atoms would have been immediately torn apart again. Had it occurred much later, the expansion might have diluted the matter so much that the formation of large-scale structure would have been impossible. The precise timing was everything. It ensured that when neutral atoms formed, they were stable, and the light they released could carry a pristine snapshot of that moment across the eons. This detailed chronology leads us to a profound question. How can we possibly measure events that occurred in the first fleeting seconds of time? The answer lies in the sophisticated tools we have built to read the faint signatures left behind. That persistent microwave hiss was a ghost in the machine at Bell Labs. Two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a massive horn antenna in New Jersey, and they could not eliminate a faint, uniform noise that seemed to come from every direction in the sky. It was present day and night through every season, an unshakable signal that defied all explanation. They meticulously cleaned the antenna, famously scraping away layers of pigeon droppings, but the noise remained. Penzias later described it as a signal that was there regardless of what we did. It was a mystery they could not solve, an annoyance that turned out to be the echo of creation itself. Unbeknownst to them, a team at Princeton University led by Robert Dick, with Jim Peebles doing the theoretical work, had just predicted the existence of a faint, cold remnant radiation from the Big Bang. When the two groups connected, the pieces fell into place with breathtaking speed. The annoying noise was the cosmic microwave background, the cooled and redshifted light from the moment the universe became transparent. This serendipitous discovery in 1965 was the smoking gun for the Big Bang theory, delivering a fatal blow to the rival steady-state model and earning Penzias and Wilson the Nobel Prize. It was the ultimate case of finding something you were not even looking for, a whisper from the dawn of time that had been bathing the Earth all along. This initial detection was just the beginning. Confirming the Big Bang required proving this radiation had the precise spectrum of a perfect blackbody, a prediction of the hot early universe. The Cosmic Background Explorer satellite, or COBE, provided that stunning confirmation in the early 1990s. Its FIRA's instrument measured the CMB spectrum and found it matched a theoretical blackbody to an astonishing accuracy of better than 0.01%. It was, as the team declared, the perfect blackbody spectrum ever measured in nature. COBE also made the first map of the tiny temperature variations, the anisotropies, across the entire sky. Later missions, the Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck Observatory, refined these maps to microkelvin precision. These exquisitely detailed charts of the infant cosmos did more than just validate the moment light escaped. They gave us our first precise measurements of the universe's fundamental parameters. From these temperature fluctuations, we could read the universe's age, 13.8 billion years, its composition of ordinary matter, and dark energy, and even the exact rate of its expansion. This data transformed cosmology from a field of grand theories into a science of precise measurement. How did we build instruments sensitive enough to capture this faint cosmic whisper? The answer lies in a relentless pursuit of technological perfection, from the humble horn antenna in New Jersey to the frigid observatories orbiting 1,000,000 miles from Earth. That faint hiss detected by Penzias and Wilson's humble antenna was just the first whisper from the cosmic dawn. To truly understand its message, we needed to amplify it, to translate its subtle patterns into a language we could comprehend. This demanded a revolution in our ability to see, a technological evolution that turned a cosmic curiosity into a precision tool for exploring the universe's infancy. The journey began with simple radio telescopes, their broad beams capturing the background's overall temperature but unable to discern its intricate details. To see the universe's blueprint, we needed to go to space, above the obscuring blanket of Earth's atmosphere. The Cosmic Background Explorer, COBE, was the first great leap, confirming the perfect blackbody spectrum and making the first blurry map of the temperature variations. It was like seeing a distant mountain range for the first time, but only as a faint, shapeless shadow. The next generation, the Wilkinson Microwave Anisotropy Probe, or WMAP, brought that range into sharper focus. Its key innovation was the use of differential microwave radiometers, instruments that constantly compared the temperature of 2 points in the sky. This brilliant design minimized systematic errors, canceling out instrumental drift and yielding exquisitely detailed all-sky maps. WMAP data allowed cosmologists to measure the universe's fundamental parameters with unprecedented precision, refining our understanding of its age, composition, and expansion rate. Yet the ultimate view came from the Planck Observatory, a marvel of cryogenic engineering. Planck's detectors were cooled to just 1/10 of a degree above absolute zero, making them exquisitely sensitive to the CMB's faint whisper. It achieved an angular resolution down to 5 arcminutes, allowing it to see features in the primordial plasma that were smaller than a full moon in the sky. Planck project scientist Jan Tauber often highlights how this resolution, combined with its multi-frequency coverage, was crucial. The observatory scanned the sky at 9 different frequencies, enabling it to meticulously separate the pristine cosmic microwave background from the foreground pollution of our own galaxy, the synchrotron radiation from spinning electrons and the thermal emission from interstellar dust. This technological cleansing revealed the CMB in its purest form. At the heart of these advanced observatories are bolometers, incredibly sensitive thermometers that measure the tiny energy deposits from individual CMB photons. Their ability to detect temperature differences of mere millionths of a degree is what allows us to read the subtle density variations from the early universe. But the story does not end with temperature. The real frontier lies in polarization, the specific direction in which the light waves oscillate. Polarization-sensitive detectors have now mapped the E-mode patterns, the gentle swirls imprinted by the primordial density waves that sloshed through the plasma. The next great quarry are the elusive B-modes, a curl-like pattern that could be the direct signature of gravitational waves from the inflationary epoch, a ripple in spacetime itself from the universe's first instant. This hunt has been a global endeavor, leveraging everything from balloon-borne experiments like Boom-Ran-G, which first confidently detected the acoustic peaks while drifting over Antarctica, to vast ground-based arrays like the Simons Observatory and the future CMB S4 project. These next-generation telescopes, with thousands of detectors working in unison, will scour the polarized sky with a sensitivity we can barely imagine today. They represent the culmination of decades of innovation, all focused on a single goal: to capture the faintest echo from the moment of creation. Who were the architects of this profound listening campaign? Behind every great cosmic discovery stands a person listening to a faint whisper. The story of recombination is not just a tale of physics, but of the brilliant and often patient individuals who deciphered its code. In the 1940s, Ralph Alpher and Robert Herman, working under George Gamow, made an astonishing prediction. After calculating how the first elements were forged in the Big Bang, they realized a remnant glow must have been left behind, a cooled radiation bathing the entire universe. They even estimated its temperature at around 5 Kelvin. Yet their profound insight was largely ignored for nearly 2 decades, a forgotten prophecy waiting for technology to catch up. George Gamow himself had laid the essential groundwork, using nuclear physics to explain the origin of the elements and setting the stage for Alpha and Herman's leap. It was James Peebles who later built the comprehensive theoretical framework for recombination itself. He detailed the intricate dance of particle physics that allowed atoms to form and photons to finally decouple, describing the process with what he called a beautiful simplicity that ties the quantum world to the vast cosmos. He often applied the Saha equation, a powerful tool from early 20th century physics, to calculate the precise moment the balance tipped. This equation allowed scientists to link the universe's dropping temperature directly to the fraction of electrons being captured by nuclei, turning a chaotic plasma into a serene gas of neutral atoms. Independently of the earlier work, Robert Dicke at Princeton had also predicted the cosmic microwave background and was building a radio receiver to hunt for it. His team was poised to make the discovery, but history had a different plan. It was the persistent, unexplained noise found by Arno Penzias and Wilson at Bell Labs that provided the accidental, crucial evidence. This confluence of prediction and serendipity transformed cosmology. Later generations of scientists then took these foundations and ran with them. David Spergel and his colleagues meticulously analyzed the data from the WMAP satellite, using the subtle patterns in the ancient light to constrain the universe's fundamental parameters with breathtaking precision, pinning down the amounts of dark matter and dark energy. The massive international teams behind the COBE and Planck observatories performed the painstaking work of mapping the anisotropies, turning theoretical predictions into a detailed chart of the infant cosmos. From Gamow's initial ideas to the thousands of engineers and scientists who built our space-based eyes, these collaborative efforts turned an abstract moment from the distant past into a testable, measurable reality. Their diverse backgrounds, from theoretical physics to electrical engineering, were all essential. How did a mathematical equation from decades prior suddenly hold the key to the universe's first moment of transparency? Those mathematical tools are the silent engines of discovery, translating the faint cosmic whisper into a language of profound insight. We can think of them as a universal clock, a set of equations that wind backward and forward through time to reveal the universe's deepest secrets. At the grandest scale, the Friedmann equations act as the master timekeepers. Derived directly from Einstein's general relativity, they describe how the fabric of the cosmos expands or contracts under the competing influences of matter, radiation, and dark energy. They are the cosmic heartbeat, dictating the rate of the universe's growth from a single, hot beginning to its vast present state. This expansion history is the first crucial input for any model of the early universe, setting the stage for everything that follows. But to understand the moment light escaped, we must zoom in from this cosmic scale to the microscopic dance of particles. This is where the Boltzmann equations take over. They are the intricate choreographers, tracking the frantic interactions between every proton, electron, and photon in the primordial soup. They model how these particles collide, scatter, and combine, governing the delicate statistical balance that slowly tipped the universe from an opaque plasma to a transparent gas. The celebrated Saha equation is a beautiful, simplified solution to this complex dance for one specific process. It acts like a precise thermometer, telling us the exact fraction of electrons that will be bound into atoms at any given temperature. It was this equation that allowed scientists like James Peebles to calculate the critical moment of recombination with such stunning accuracy. Yet the real world is always more complex than our simplest models. The first pass of recombination would release a flood of energetic photons, including many in the Lyman alpha line, which could easily knock a neighboring electron right back out of its atom, slowing the entire process. This is where sophisticated computer codes like RecFast come into play. They are the digital laboratories where these subtle effects are accounted for, meticulously simulating the trapping and reabsorption of these photons to produce a detailed timeline of how the cosmic fog lifted over tens of thousands of years. Cosmologists like Wayne, who have built entire careers on these foundations, using these integrated models to predict the precise pattern of hot and cold spots we should see in the cosmic microwave background. The result is a theoretical power spectrum, a graph of expected temperature variations across different angular scales. The fact that this predicted curve matches the exquisitely detailed measurements from Planck and WMAP with such phenomenal precision is one of the greatest triumphs of modern science. It is a direct validation that our mathematical understanding of the universe's first 400,000 years is fundamentally correct. These models also quantify the journey of light itself through the integral of optical depth. This mathematical expression tallies up the probability that a photon would be scattered at any point on its trip from the early universe to our telescopes. As recombination progressed, this optical depth plummeted, and the integral reveals the exact history of the universe's transition from opaque to transparent. Furthermore, the tiny fluctuations we observe are perfectly explained by cosmological perturbation theory, which describes how those initial quantum seeds from inflation grew under the relentless pull of gravity. What happens when we introduce the mysterious influences of dark matter and dark energy into these equations? Dark matter, which does not interact with light at all, dominated the gravitational landscape even during recombination. Its presence modified the growth of those primordial density perturbations, shaping the specific heights of the acoustic peaks in the CMB power spectrum. Dark energy, acting as a repulsive force, influences the expansion rate in the later universe, which in turn affects how we interpret the light from the most distant sources. These mathematical frameworks are not just historical records. They are predictive engines allowing us to run simulations that test how the cosmic microwave background would appear if the universe had more dark matter, less ordinary matter, or a different expansion rate. They even let us forecast the observable imprint of later events, like the Epoch of Reionization, when the first stars and galaxies lit up and began to tear apart the neutral hydrogen atoms once more. The greatest challenge in this entire endeavor lies in modeling non-equilibrium processes, moments when the universe changed too rapidly for matter and radiation to maintain a perfect thermal balance. Capturing these fleeting instants requires immense computational power and deep physical intuition, pushing our mathematical tools to their absolute limits. This entire intricate framework exists for one ultimate purpose: to interpret the faint signals from the past. So what are the specific, observable consequences of recombination that these models help us decode? That map of the cosmic microwave background is a photograph of the universe's first sound. Every hot and cold spot is a frozen note in a cosmic symphony, a snapshot of the rhythmic sloshing that filled the cosmos before the great silence fell. These anisotropies, these temperature variations of just a few millionths of a degree, are the amplified echoes of quantum seeds stretched across the sky. They are not random. They form a specific pattern of peaks and troughs, a harmonic signature we call the angular power spectrum. The first and most prominent peak in this spectrum tells us something profound about the shape of our universe. Its specific angular size reveals that the cosmos is geometrically flat. On the largest scales, parallel lines will never meet, and the rules of Euclidean geometry we learned in school hold true across the vast expanse of space. This flatness is a direct consequence of the total density of the universe, a precise balance between matter, radiation, and the mysterious push of dark energy. The subsequent peaks are equally revealing. The second peak's height is exquisitely sensitive to the density of ordinary matter, the baryons. Its measured value confirms that the atoms making up stars, planets, and us constitute less than 5% of the cosmos. The third peak gives us the density of the invisible scaffolding, dark matter, which makes up about 27% and whose gravity was the primary force shaping those early ripples. The precise calibration of these peaks by the Planck collaboration acts like a cosmic barcode, constraining fundamental parameters with staggering precision. We can read the universe's expansion rate, the Hubble constant, and the exact ratio of protons to photons from this ancient light. But how do these tiny temperature differences actually arise? A photon escaping a slightly denser region of the early plasma had to climb out of a deeper gravitational well. This struggle cost it energy, stretching its wavelength and making it appear cooler to our telescopes. This is the Sachs-Wolf effect, the primary reason we see large-scale cold spots on the map. At smaller scales, we witness the direct imprint of motion. The Photon-Baryon fluid was oscillating, with regions compressing and heating, then rarefying and cooling. A hotspot might be a region that was maximally compressed at the moment of last scattering, its photons boosted by the pressure. A cold spot could be a region that had just reached its maximum expansion. The Doppler effect from this fluid motion also left its mark, shifting the light's frequency as it moved toward or away from us. Beyond temperature, the very way this light waves holds a deeper story. When the last scattering occurred, the photons were polarized by their final interaction with electrons. This created a distinct pattern known as E-mode polarization, a gentle, curl-free arrangement that mirrors the density variations, confirming the plasma was indeed a fluid of light and matter sloshing together. The holy grail of this field, however, is the detection of a primordial B-mode polarization. This swirly, curl-like pattern would be the smoking gun for inflation, a direct imprint of gravitational waves rippling through spacetime itself in the universe's first instant. While faint hints of this signal have been reported, its definitive discovery remains one of cosmology's greatest quests. These anisotropies are the ultimate cosmic fossil. They are the gravitational blueprint from which all structure grew. Every galaxy cluster, every vast cosmic void, finds its origin in one of those tiny temperature fluctuations. The cold, slightly denser spots provided the extra gravitational pull that, over billions of years, gathered the dark matter and then the ordinary gas to form the first stars and the majestic galaxies we see today. This intricate map is not just a picture of the past. It is a living document, a testament to how the universe translated microscopic quantum jitters into the grand tapestry of the cosmos. Dark matter was the silent architect of the cosmic dawn, an invisible hand guiding the light's great escape. While ordinary matter was locked in a violent dance with radiation, dark matter remained aloof, untouched by the searing photons. It did not scatter, absorb, or emit light. Its only tool was gravity, and that was more than enough. From the universe's earliest moments, dark matter began to form a vast, invisible scaffolding. This cosmic framework grew steadily, its gravitational wells deepening, patiently waiting for the ordinary matter to catch up. This difference in behavior created a profound divergence in their evolution. Baryons, the protons and electrons, were trapped in the Photon-Baryon fluid, pushed and pulled by radiation pressure. But dark matter simply clumped, its structures growing faster and sooner, setting the stage for everything to come. The evidence for this invisible component emerged not from the primordial universe, but from our own galactic backyard. Astronomer Vera Rubin's meticulous work on galaxy rotation curves revealed a stunning anomaly. Stars at the outer edges of galaxies were orbiting far too quickly. If only visible matter were present, those stars should have been flung away into the void. Something unseen, a vast halo of dark matter, was providing the extra gravitational glue to hold these galaxies together. This discovery grounded a cosmic mystery in observable reality. Cosmologists soon wove dark matter into the standard model of the universe, known as the lambda CDM model. Its influence is permanently etched into the cosmic microwave background. Look at the third peak in the CMB power spectrum. Its specific height is a direct measure of the dark matter density. Here is why. Those primordial sound waves were a battle between gravity and pressure. Dark matter's gravity pulled baryons into its wells, but radiation pressure pushed them out. The first acoustic peak largely tells us about the geometry of the universe. The second peak reveals the density of ordinary matter, but the third peak is where dark matter's role becomes crystal clear. Because dark matter does not feel radiation pressure, it could collapse into dense clumps long before recombination. Its deep gravitational potentials acted like anchors, making it harder for the baryon photon fluid to oscillate outward after being pulled in. This suppression of the fluid's motion on smaller scales imprinted itself on the third peak, giving us a precise reading of dark matter's abundance. What if dark matter interacted with ordinary matter more strongly? The pristine nature of the CMB tells us the answer. Any significant non-gravitational interaction between dark matter and baryons would have left a smudge on the cosmic microwave background, a subtle distortion in its temperature patterns. The fact that we see no such distortion places incredibly tight constraints on these possible interactions. They must be extraordinarily weak, confirming dark matter's ghostly nature. This invisible component was the essential ingredient that ensured our universe was not perfectly smooth. It amplified the tiny quantum fluctuations from inflation, providing the gravitational seeds into which ordinary matter would later flow. After recombination, neutral hydrogen gas slowly began to coalesce within these dark matter halos. It was within these cosmic cradles, millions of years later, that the first stars would ignite, ending the cosmic dark ages and lighting up the universe for the very first time. Without dark matter's steadfast gravitational pull, those first structures might never have formed, leaving the cosmos a dark and endless sea of featureless gas. That frozen sound wave left a permanent ruler etched across the cosmos. When the great decoupling happened, the rhythmic sloshing of the Photon-Baryon fluid suddenly stopped. The compressions and rarefactions, those acoustic oscillations, were instantly locked into the distribution of matter. This created a specific, measurable scale known as the sound horizon. At the moment of recombination, this was the farthest distance a sound wave could have traveled from the beginning of time, roughly 500,000 light-years across. Today, because of the universe's expansion, that same frozen wave has been stretched to a scale of nearly 500 million light-years. It is this immense yardstick, this baryon acoustic oscillation, that astronomers now use to measure the geometry and expansion history of the universe itself. We see its signature in the grand maps of the cosmos. When scientists with projects like the Sloan Digital Sky Survey and its BOSS program chart the positions of millions of galaxies, they do not find a random scatter. There is a subtle statistical preference for galaxies to be separated by this specific distance. It is as if the universe has a preferred note, a fundamental frequency visible in the large-scale structure, a faint echo of that primordial symphony. This standard ruler is incredibly powerful because it does not rely on the brightness of objects, which can be tricky to calibrate. It relies purely on geometry. By measuring the apparent size of this BAO ruler in the nearby universe and comparing it to its size in the distant, younger universe, we can track how the fabric of space has stretched over billions of years. These measurements provided independent, stunning confirmation that the universe's expansion is accelerating, driven by the mysterious force of dark energy. The same sound horizon that defines the peaks in the cosmic microwave background power spectrum is the very same scale we see imprinted in the distribution of galaxies. The CMB gives us a picture of the ruler at the moment it was made, while the galaxy surveys show us how that ruler has been stretched over cosmic time. Together with other probes like distant supernova, baryon acoustic oscillations form a third, crucial leg of a tripod, solidifying our modern cosmological model. They tell us not only that the universe is expanding, but exactly how that expansion has changed. Do these oscillations hold a clue to the ultimate fate of everything? By tracing this acoustic legacy, we can project the expansion forward, testing whether dark energy will remain constant or evolve, gently pulling the universe apart or perhaps even tearing it to pieces. This cosmic echo connects the first moment of transparency directly to the universe we see around us, a bridge of sound that leads to the next great cosmic transition, when the dark ages ended and the first stars blazed to life. The cosmic dark ages did not last forever. After hundreds of millions of years of profound silence, a new light began to stir. The first stars and galaxies ignited, flooding the universe with a fierce, ultraviolet glare that tore through the neutral hydrogen gas. This was the Epoch of Reionization, a second great transformation that rewrote the cosmic story. The very atoms of hydrogen, which had formed so peacefully during recombination, were now being violently ripped apart once more. Their electrons were stripped away, returning the universe to a tenuous, ionized plasma. It was not the thick, opaque fog of the primordial era, but a diffuse, misty state that introduced a faint new opacity across the cosmos. This process unfolded over hundreds of millions of years, beginning around 150 million years after the Big Bang and largely concluding by the 1 billion year mark. It was driven by the first brilliant, massive stars and the intense radiation from early quasars, whose powerful beams acted like cosmic blowtorches, carving out vast, ionized bubbles in the surrounding darkness. Experts like Abraham Loeb have modeled how these first structures provided the flood of ionizing photons, a torrent of energy sufficient to tear electrons from their atomic orbits on a cosmic scale. This rescattering of light left its own unique fingerprint on the cosmic microwave background. As CMB photons traveled through this newly ionized medium, a small fraction of them, perhaps 5 to 10%, collided with the freshly freed electrons. This late-time interaction imprinted a specific signature on the light's polarization. The large-angle E-mode polarization patterns we observe today are a direct echo of that rescattering event. By measuring the precise characteristics of this signal, missions like Planck have been able to estimate the Thompson optical depth, a value around 0.05, which tells us the total column density of free electrons that these ancient photons encountered on their long journey to us. This measurement suggests reionization was not a single cataclysmic event, but a gradual and complex process, likely beginning with small, isolated bubbles of ionized gas that eventually grew and overlapped to fill the entire universe. This second chapter of ionization connects the pristine primordial universe directly to the dawn of structure. The invisible scaffolding of dark matter was absolutely essential, its gravitational wells providing the nurseries where the first galaxies could coalesce and generate the ferocious radiation needed to reionize the cosmos. The quest to directly witness this cosmic dawn is now a primary goal for the James Webb Space Telescope. By peering back to those incredibly distant epochs, it aims to spot the very first galaxies and quasars that brought an end to the Dark Ages. Reionization fundamentally altered the CMB, adding a final, faint layer to its story. This phase marks the ultimate transition from a simple, smooth universe to the complex, structured cosmos we inhabit today, a bridge of light between the first atoms and the first stars. The faint whisper of the cosmic microwave background holds a deeper layer of secrets, one written not in temperature, but in the very direction its light waves oscillate. This polarization is the ultimate prize, a signal over 1,000 times fainter than the temperature variations we have mapped so beautifully. To detect it is like trying to hear a single soft note in a roaring symphony. Primary signals are called E-modes and B-modes. E-modes are gentle, curl-free patterns, a direct imprint of the density waves that sloshed through the primordial plasma during recombination. They confirm the universe was indeed a fluid of light and matter. But B-modes are the true holy grail, a swirly, curl-like pattern that could be the direct signature of gravitational waves from the universe's inflationary birth. Finding them requires not just sensitive instruments, but a monumental act of cosmic cleaning. Our own Milky Way galaxy is a brilliant and messy foreground. Synchrotron radiation from electrons spiraling around magnetic fields fills the sky with polarized light. Thermal emission from interstellar dust grains, aligned by those same magnetic fields, creates another pervasive polarized haze. These galactic signals are not just noise, they are a bright veil obscuring the pristine cosmic signal beneath. Scientists like Ko Lin Kuo have led the charge to build the tools for this hunt. Advanced bolometers, chilled to a fraction of a degree above absolute zero, form the heart of telescopes at the South Pole like the BICEP and Keck array. These detectors are so sensitive they can measure the minuscule energy deposit of individual CMB photons. But sensitivity alone is not enough. The greatest challenge lies in separating the cosmic truth from the local illusion. This was starkly illustrated in 2014 when the BICEP-2 team announced a thrilling detection of primordial B modes. The cosmology world held its breath. Yet, further analysis in collaboration with the Planck satellite revealed a sobering reality. The signal they detected was largely contaminated by polarized dust from our own galaxy. It was a powerful lesson in humility and the absolute necessity of multi-frequency observations. By scanning the sky at many different wavelengths, experiments can build a spectral fingerprint of each foreground. Galactic synchrotron radiation has a distinct signature, while interstellar dust emits differently. By mapping these foregrounds across multiple frequencies, cosmologists can create a detailed model and subtract them away, like carefully peeling back layers to reveal the faint image underneath. Beyond the galactic pollution, the instruments themselves introduce challenges. Tiny imperfections in a telescope's optics, such as beam asymmetries, can themselves create spurious polarization signals that mimic the cosmic ones. Mitigating these systematics requires brilliant engineering and relentless calibration. The entire pursuit is a testament to perseverance, pushing technology to its limits in the most extreme environments on Earth. What new technologies might finally resolve these issues? The next generation of experiments, like the Simons Observatory and CMB S4, will deploy tens of thousands of these advanced detectors, creating an unprecedented map of the polarized sky. Their success hinges on even lower temperature cryogenics to reduce instrumental noise and sophisticated multi-frequency designs to isolate the cosmic signal. This painstaking work does more than test inflation. It forces us to consider the very foundations of our cosmic story. If the primordial B modes remain elusive, could alternative theories of the early universe beyond inflation provide a better explanation? The quest to read this final page of the cosmic dawn continues, a delicate dance between human ingenuity and the universe's faintest echoes. Our map of the infant cosmos is incredibly precise, yet its very perfection pushes us to ask what lies beyond it. Cosmologists are actively exploring theories that stretch past the standard Big Bang narrative, considering universes that cycle through endless collisions or realities built from vibrating strings. These alternatives are not mere speculation. They make specific, testable predictions about the cosmic microwave background, challenging us to look closer at the data. The Turok-Steinhardt cyclic model, for instance, proposes a universe without a beginning, where our Big Bang was preceded by an earlier phase of contraction and a bounce. This model predicts a distinct signature in the CMB polarization, a specific pattern of gravitational waves that would look different from those generated by standard inflation. Other theories suggest the fundamental constants of nature, like the fine structure constant, might have been different in the early universe. Such a change would have directly altered the timeline of recombination, shifting the precise moment electrons bonded to protons and leaving a subtle mark on the power spectrum we observe. Experts like Paul Steinhardt have critiqued the inflationary model for its requirement of extreme fine-tuning, arguing that some alternatives offer a more elegant and natural explanation for the universe we see. The search for evidence often focuses on non-Gaussianities, which are subtle deviations from the simple, bell curve-like statistics of the CMB temperature fluctuations. The standard model predicts these fluctuations should be almost perfectly Gaussian, but some alternative theories forecast specific, measurable twists in this statistical pattern. Similarly, the hunt for primordial B modes is not just about finding them, but about reading their specific character. Different theories of the early universe predict different patterns in this swirly polarization, meaning the detailed shape of the signal could point to one cosmic origin story over another. Current observations of the CMB's statistical properties have tightly constrained many of these ideas, ruthlessly eliminating models that do not align with the exquisite data from Planck and other observatories. This process often invokes Occam's razor, the philosophical principle that the simplest explanation consistent with the evidence is usually the best. So far, the standard lambda CDM model, with its single episode of inflation, remains the simplest framework that fits the vast majority of our observations. Yet the pursuit of alternatives is far from a futile exercise. It is the engine of scientific progress, driving innovation in both theoretical cosmology and the technology of our telescopes. What if the next generation of experiments, like CMB S4, reveals a glaring anomaly in the CMB that our current model cannot explain? The entire foundation of our cosmic story would be shaken, forcing a profound and thrilling revision of everything we think we know. This exploration bridges our quest for data with a deeper philosophical wonder, reminding us that the universe's first light may still hold secrets capable of overturning our most cherished assumptions. That faint cosmic whisper does more than just reveal physical laws. It forges a profound connection between human consciousness and the cosmos itself. We are essentially looking back in time, witnessing the moment our universe became transparent, and in doing so, we are confronting our own origins. This ability to decode events from nearly 14 billion years ago using only mathematics and observation speaks to a deep, almost mysterious intelligibility woven into the fabric of reality. The universe, it seems, can be understood. This very fact touches on a profound philosophical concept known as the anthropic principle. It asks a staggering question. Are the fundamental constants of nature, the strength of gravity, the mass of an electron, perfectly fine-tuned just so that a universe like ours, with stars, planets, and conscious life, could eventually emerge? Consider the precise timing of recombination. Had the universe expanded just a fraction faster, matter would have been too diluted for galaxies to form. Had it been slower, it might have collapsed back on itself long before life could arise. We find ourselves in a universe with parameters that seem curiously suited for our existence. This is not necessarily proof of design, but it is a compelling puzzle that forces us to consider our place in the grand scheme. The iconic words of Carl Sagan capture this elegantly. He said, "We are a way for the cosmos to know itself. The atoms that form our bodies, the iron in our blood, the calcium in our bones, were forged in the hearts of long-dead stars. But the very hydrogen in the water we drink is a direct relic from the Epoch of Recombination. We are not just in the universe is in us." This realization inspires a powerful existential awe, a sense of unity with a cosmos that is both vast and ancient. Gazing at the map of the cosmic microwave background, with its profound uniformity, also pushes our imagination toward the edge of known physics. Why does the universe appear so similar in all directions? This question leads some to speculate about a multiverse, a vast collection of universes, each with its own unique set of physical laws, with ours being just one where the conditions were accidentally right for us to be here. This knowledge also instills a necessary cosmic humility. The entire history of our species is a mere blink in cosmic time, and our world is a tiny, fragile speck in an immense void. This perspective can dissolve terrestrial conflicts and remind us of our shared journey on this pale blue dot. It fuels an insatiable drive to explore, to push further out into the darkness, driven by the same curiosity that allows us to decipher the first light. How does this change our view of purpose? It suggests that our purpose may be found in the seeking itself, in the act of asking questions and building a collective understanding that transcends any single culture or generation. We are united by a shared cosmic heritage, a story that begins with a great escape from a primordial fog and continues with us here and now, trying to read its opening chapters. The same cryogenic systems that chill CMB detectors to a whisper above absolute zero are now refining magnetic resonance imaging machines. To capture the universe's faintest light, we had to push the boundaries of cold, developing intricate helium dilution refrigerators and advanced adiabatic demagnetization techniques. These are not just laboratory curiosities. The precise temperature control required for a telescope like Planck directly improves the thermal management of superconducting magnets in hospital MRI scanners, leading to sharper diagnostic images and earlier detection of disease. This technological transfer is a quiet revolution born from our need to see the cosmic dawn. The heart of this effort is the bolometer, a device so sensitive it can measure the minuscule energy of a single microwave photon. Originally perfected for CMB observatories, these ultra-sensitive thermometers now form the core of new thermal imaging cameras. These cameras see heat signatures with stunning clarity, allowing firefighters to locate people through dense smoke and enabling security personnel to detect threats in total darkness. The same low-noise amplifier technology developed for telescopes like the Cosmic Background Imager has been adapted to improve signal clarity in wireless communication networks, giving you a stronger, more reliable cell phone connection. Even the way we process data has been transformed. The monumental challenge of extracting a cosmic signal from a sea of galactic noise pioneered new techniques in statistical analysis and machine learning. Cosmologists facing a problem of unimaginable scale became experts in pattern recognition. The algorithms they wrote to find subtle temperature variations in the CMB are now used to identify patterns in complex genetic data, spot early signs of financial fraud in global markets, and train artificial intelligence to recognize faces and objects. Nobel laureate John Mather, who led the COBE mission, often emphasizes that building a tool to answer one profound question invariably unlocks solutions to 100 others we had not yet thought to ask. The precise frequency standards we derive from cosmological observations now calibrate the atomic clocks that underpin the entire global positioning system. Without that foundational work in measuring the universe, the pinpoint navigation in your car or smartphone would be far less accurate. We are standing on the brink of even greater breakthroughs. The relentless drive for more sensitive CMB detectors is accelerating the entire field of quantum sensing. New materials discovered in the quest for perfect superconductors are finding their way into potential quantum computers, machines that promise to solve problems beyond the reach of any classical computer. What seems like a purely philosophical pursuit to understand the first moment of time consistently propels our technology forward in unexpected and profoundly human ways. This practical legacy bridges the gap between the abstract cosmos and our daily lives, revealing that the tools we build to explore the heavens often become the instruments that heal, connect, and protect us here on Earth. That baby picture of the universe now hangs in digital planetariums and classroom displays worldwide. Educational outreach has transformed this profound cosmic moment into a story everyone can grasp. Imagine a child touching an interactive screen, watching as a brilliant, opaque universe suddenly clears with photons streaming free for the first time. Museums have built entire exhibits around this narrative, with hands-on displays that let visitors physically manipulate models of the Photon-Baryon fluid, feeling the tension between gravity and radiation pressure. Documentaries like the rebooted Cosmos series take viewers on a visual journey, using state-of-the-art animation to make the invisible dance of electrons and protons during recombination a breathtaking spectacle. Neil deGrasse Tyson often frames this as the universe's greatest coming-of-age story, a pivotal moment of transparency after a long childhood of darkness. He calls the cosmic microwave background the ultimate family photo, a portrait of our cosmic ancestors from a time long before the Earth even existed. This powerful metaphor sticks in the mind far longer than any complex equation. Online, the doors are thrown wide open. Universities like MIT and Stanford offer free course modules that break down the Saha equation and the physics of decoupling into digestible, step-by-step lessons. The beautiful, swirling all-sky maps from the Planck satellite are not locked away in research papers. They are available for anyone to explore, allowing students to hunt for the same acoustic peaks that professional cosmologists study. Citizen science projects invite the public to participate directly, classifying galaxy shapes or even helping to analyze subtle features in CMB data, turning passive observers into active contributors. Social media campaigns distill these monumental ideas into captivating 60-second videos and infographics, asking questions like, what color was the universe when it was born? These efforts do more than just share facts. They build a bridge between the abstract frontier of cosmology and everyday curiosity. By making the Epoch of Recombination relatable, we inspire the next generation of engineers, physicists, and dreamers. This widespread understanding cultivates a society that values evidence, reason, and our shared cosmic heritage. How will these newly inspired minds shape the next great chapter of discovery? The future of cosmic exploration depends not just on the tools we build, but on the collective wonder we nurture today. These colossal new observatories are humanity's next great listening posts, designed to capture the faintest murmurs from the cosmic dawn. The CMB S4 project, a ground-based array planned for the late 2030s, represents a staggering leap in scale. It will deploy hundreds of thousands of individual detectors across sites in the high Chilean Andes and the pristine darkness of the South Pole. This distributed network will function as a single, colossal ear, aiming to map the polarization of the cosmic microwave background down to the nanokelvin scale, a sensitivity 1,000 times greater than our current capabilities. At the heart of this quest is the hunt for primordial B modes, the swirly polarization pattern that is the direct signature of gravitational waves generated during inflation. Detecting this signal would be more than just confirming a theory. It would be our first direct observational window into the era of quantum gravity, a realm where gravity itself behaves as a quantum force. These gravitational waves are essentially ripples in the very fabric of spacetime, shaken loose by the violent birth of the cosmos. The project's co-director, John Karlstrom, emphasizes that this is not an incremental improvement, but a transformational one, pushing into a new regime of precision cosmology. Alongside this grand hunt, missions like the Simons Observatory, led by experts like Suzanne Staggs, are already paving the way. Its arrays of small aperture telescopes will scour the sky for these elusive signals, while also searching for light relics, hypothetical particles left over from the Big Bang that have so far evaded every other form of detection. These international collaborations, uniting scientists from dozens of countries, are also targeting other subtle anomalies. Future data may reveal non-Gaussianities, specific statistical twists in the temperature map that could point to new physics operating in the universe's first instance. They will also hunt for spectral distortions, tiny deviations from the perfect Blackbody curve of the CMB. Finding such a distortion would be like discovering a fingerprint on a pristine artifact, evidence of a violent event, like the explosive formation of the first black holes that occurred after recombination but left a permanent mark on the ancient light. These measurements will do more than test inflation. They will precisely measure the total mass of neutrinos, those ghostly particles that flood the universe, and provide new, independent constraints on the nature of dark energy. The sheer volume of data from these projects is incomprehensible, requiring exascale computing and sophisticated simulations to even interpret. What if the signals we find do not match any of our current models? The next decade of observation promises to either cement our standard cosmological story or force a rewrite of the universe's first chapter, revealing surprises from its deepest infancy that we cannot yet even conceive. These virtual universes are our cosmic laboratories, running not on chemicals and glassware, but on pure mathematics and silicon. To understand the faint patterns in the ancient light, we must recreate the entire early cosmos inside a supercomputer. Codes with names like CMB Fast CAM and Class are the engines of this digital creation, simulating the universe's journey from its first quantum shudders all the way to the great liberation of the CMB. They begin with a set of initial conditions, a digital seed of quantum fluctuations, and then let the laws of physics play out across billions of virtual light years. The goal is to produce a mock cosmic microwave background map, a synthetic sky that we can hold up against the real one from the Planck satellite. If they match, we know our understanding of the underlying physics is sound. These simulations are staggeringly complex, integrating equations for radiative transfer that track how light moves through the primordial plasma, modeling the delicate atomic transitions as electrons jump between energy levels, and accounting for the slow, gravitational clustering of dark matter that provides the scaffolding for everything to come. To handle the inherent randomness of processes like photon scattering, cosmologists employ Monte Carlo methods. This technique uses random sampling, like rolling cosmic dice millions of times, to model the probable paths of photons and the statistical outcomes of particle collisions, building up a realistic picture from countless individual random events. The real power of these virtual universes lies in their malleability. Researchers like Anthony Lewis, a key architect of the CAM code, use them to run sensitivity analyzers. They can dial the Hubble constant up or down, adjust the mass of neutrinos, or change the amount of dark matter, and then watch how the simulated CMB power spectrum morphs in response. This process is how we fit our models to the real data, precisely estimating the values of these fundamental constants and quantifying our uncertainties. For example, these detailed simulations revealed a subtle but crucial delay in recombination itself. The first hydrogen atoms to form would release a flood of Lyman alpha photons, which are particularly energetic. These photons could then travel through the plasma and knock electrons right back out of other newly formed atoms, like a game of cosmic pinball. Modern recombination codes meticulously simulate this trapping and reabsorption of radiation, showing that the process of atom formation was not a clean, instantaneous switch, but a slightly drawn-out statistical battle. Simulating such non-equilibrium physics, where matter and radiation fall out of perfect thermal balance, remains one of the grand challenges in cosmology. It requires immense computational power and deep physical insight to capture these fleeting, chaotic moments accurately. Now, machine learning is being integrated to accelerate this work, with neural networks learning to emulate the behavior of these vast simulations, producing results in minutes that would otherwise take supercomputers days to calculate. This synergy between silicon and sky is what drives our progress. We build a virtual cosmos, test our theories within it, and then look up to see if the real universe agrees. What new doors might open if we could run these simulations on a quantum computer, harnessing quantum mechanics itself to model its own primordial story? This relentless cycle of prediction and observation does more than just illuminate the past. It gives us the confidence to project forward, to run the simulation in reverse and ask the most profound question of all. Where is this entire cosmic journey ultimately headed? That first great escape of light did more than just illuminate the cosmos. It wrote the first sentence of a story whose final chapter is the end of everything. The precise conditions frozen into that ancient glow, the density of matter and the geometry of space, are the very same parameters that now govern the universe's ultimate fate. Every whisper of temperature variation in the cosmic microwave background is a piece of a cosmic clock, ticking not just from the past but toward the future. The stunning flatness of the universe, so clearly revealed by the first acoustic peak, tells us the total density of the cosmos is very close to the critical value. This delicate balance, a legacy of the inflationary epoch, is the primary reason our universe is set on a path of perpetual expansion, a trajectory that began its influence during those very first moments of transparency. The Lambda CDM model, which is our standard guide to cosmic evolution, is built directly upon the foundation of CMB measurements. This model points toward a specific and somber destiny, the Big Freeze. In this future, the expansion driven by dark energy continues unchecked. Galaxies will drift ever farther apart, their light eventually redshifted beyond detectability. The last stars will exhaust their nuclear fuel and wink out one by one. Over trillions of years, the cosmos will become a vast, dark, and profoundly cold void. Physicists like Sean Carroll describe this as the inevitable victory of entropy, where the universe reaches a state of maximum disorder and all organized activity, from star formation to life itself, becomes impossible. The baryon density, a number we read directly from the second peak of the CMB power spectrum, plays a crucial role in this long-term forecast. It dictated how much raw material was available to form stars and galaxies. A higher density might have led to a universe that burned through its stellar fuel more quickly, hastening the arrival of the Dark Ages. A lower density might have prevented large galaxies from ever forming at all. The value we observe set a specific timer on the era of cosmic light and life. Even dark energy, the mysterious force driving the acceleration, has its origins subtly linked to those initial conditions. While its nature remains one of physics' greatest puzzles, its dominance today was a possibility encoded in the universe's infancy. The CMB data rules out other, more violent endings. The measured flatness tells us a big crunch, a catastrophic recollapse of the universe, is incredibly unlikely. The precise uniformity of the background radiation also places tight constraints on the possibility of a big rip, a scenario where dark energy grows so powerful it tears apart galaxies, stars, and even atoms themselves. While not entirely impossible, the data strongly favors the slower, more gradual decline of the Big Freeze. This cosmic perspective ties the moment of creation's first transparency directly to its final silence. It means that the same event that allowed us to see the universe also contains the blueprint for its end. What does this mean for the possibility of life in the far future? In a cosmos destined for cold and darkness, the window for conscious beings to arise and comprehend their own story is finite, a brief, bright flicker between the first light and the final, eternal night. This profound connection invites us to see cosmology not as a series of disconnected events, but as a single, unified narrative stretching from the birth of light to the death of time. This grand cosmic story is woven from threads drawn from every corner of science. The moment light escaped is not just an astronomical event, it is a masterpiece of interdisciplinary collaboration, where the laws of the impossibly small meet the history of the impossibly large. Particle physicists provide the script for the universe's first acts, detailing the fundamental interactions within that searing primordial plasma. They define the rules of engagement for every particle and force. Astronomers then capture the final performance, observing the cosmic microwave background and the vast large-scale structure of galaxies, the direct outcome of those ancient processes. And chemists play a crucial role in the middle act, informing our understanding of the delicate atomic transitions as electrons settled into their orbits around hydrogen and helium nuclei. This synergy is profoundly practical. Our most precise models of recombination rely on laboratory measurements of atomic cross-sections, data painstakingly gathered by chemists and atomic physicists. These numbers tell us the exact probability that an electron will be captured by a proton, turning an abstract cosmic moment into a calculable statistical event. Similarly, our knowledge of Big Bang nucleosynthesis is grounded in nuclear physics data from particle accelerators, which replicate the fierce energies of the universe's first 3 minutes to see how deuterium and helium were forged. This cross-pollination of ideas pushes the boundaries of imagination. Theorists like Lisa Randall work at this thrilling intersection, exploring how concepts from string theory, such as extra dimensions, might leave subtle, detectable imprints in the polarization patterns of the cosmic microwave background. Even the precise timing of recombination hinges on quantum mechanical calculations of atomic energy levels, a beautiful bridge between the micro and macro worlds. The ripple effects extend even further. Geologists and planetary scientists use the robust cosmic timeline, anchored by the CMB, to precisely date events in our own solar system's formation. Biologists, in turn, consider the cosmic conditions necessary for life, pondering how the specific outcome of recombination set the stage for a universe that could one day become self-aware. How can we foster more of these cross-field collaborations? The answer lies in building conversations between specialists, creating spaces where a chemist's detail-oriented precision can illuminate an astronomer's grand vision. This unified endeavor reveals that the cosmos cannot be understood through a single lens. Its story demands that we bring all of our knowledge together, listening to the faint echo of creation with every tool at our disposal. That first cosmic dawn was not a single event, but the magnificent finale of a long chain of physical transformations. From the frantic forging of atomic nuclei in the first 3 minutes to the gradual, meticulous capture of electrons hundreds of thousands of years later, each step was an essential link in the chain that led to transparency. This epic journey from a searing, opaque fog to a universe flooded with free light showcases the profound power of scientific inquiry. It is a story woven from the threads of bold theory, painstaking observation, and brilliant technology, all converging to illuminate an event that occurred nearly 14 billion years ago. There is a deep humility in realizing that the ancient light washing over our telescopes today began its long journey when the cosmos itself was in its infancy. Its detection is a testament to human perseverance, to the generations of scientists who pieced together this grand narrative from the faintest whisper in the static. Albert Einstein once reflected that the most incomprehensible thing about the universe is that it is comprehensible. The fact that we can point to a map of the cosmic microwave background and see the validated imprint of primordial sound waves is the ultimate expression of that idea. We have turned a beautiful abstraction into empirical fact. This knowledge forges a powerful connection, reminding us that we are not just inhabitants of the cosmos but active participants in its unfolding story. Our curiosity and wonder are the very tools that allow us to reach back across the eons and witness our own origins. This reflection is not an end point. It is a foundation. How will future generations, armed with even more powerful tools and this incredible legacy, build upon our understanding of the universe's first great transition? We have traced the universe from a superheated prison of light to its great liberation, a moment etched forever into the cosmic microwave background. This story of recombination reveals a cosmos of profound elegance, where precise conditions allowed simple atoms to form and light to finally stream free. It underscores a remarkable truth. Our human ingenuity has allowed us to decode this ancient sequence, from the quantum ripples that seeded all structure to the vast galactic webs they spawned. The entire cosmic narrative, from the first hydrogen atom to the last distant quasar, is connected back to that foundational event. This understanding transforms a glance at the night sky into something deeply personal. We are not merely looking at points of light, we are witnessing a history, receiving photons that have journeyed across the eons, a direct link to the universe's moment of transparency. This journey is far from over. I would love to hear which part of this cosmic story resonated most with you, so feel free to share your thoughts below. If you want to join us as we unravel more of space's greatest mysteries, be sure to subscribe. Our exploration continues because every answer we find simply reveals new, more thrilling questions